So the first thing we always want to do is to give a quick sketch. Be sure that you label all your axes and give your graph a title. So this will be shipping charge. And our x-axis represents weight, but this time our weight is measured in pounds. I'll abbreviate LBS. And our y-axis is going to be cost, and we're measuring our cost in dollars. It says if we go from 0 to 5 that there's a flat rate charge of $6 there. Now, I'm not going to draw the open-closed interval signs just for convenience sake, just to get a quick graph. If I go from 5 up to 10, then the jump goes from $6 up to $9. So anything in that interval there costs $9. The next 5-pound increment from 10 to 15 will cost me $12. And so I could continue the graph if I needed to, but I see enough that I know what my equation is going to look like. So my equation will be shipping charges, so maybe S for shipping, and you can call it F or Y or whatever you want to call it, but it's a step function and there's no left-right shift, so I don't need a parenthesis with an add-subtract, because the add-subtract would make the left-right shift. I don't need that, but I do need to make my steps 5 times as long. So that's the inside inverse multiplier. So to make my steps 5 times as long, I use the inverse 1/5. I need my first step not to come out of 0, 0, but my first step needs to be shifted up 6. And when my steps jump, they jump 3 times bigger than normal. A normal jump would be 1, but this jumps from 6 to 9, that's a jump of 3, or from 9 to 12, again a jump of 3. So I have a 3 multiplier there. So the next one is relative to parking. And a lot of parking lots, like airport parking lots, will do this. So my graph, cost of parking, and as soon as I pull through the gate and they give me a ticket, if I just turn right around right then, they'll go ahead and charge me for the full hour. So this will be time measured in hours, and the axis will be cost, the y-axis, cost measured again in dollars. And so anything up to 1 hour, just automatically, I have to pay $3. But if I go over 1 hour, even if it was 1 hour and 1 second, the ticket that punches just automatically adds another $1.50, and so I'm up to $4.50. And so everything in that interval from 1 to 2 is all charged $4.50. And then if I go over 2 hours, and so between 2 and 3, it just automatically adds another $1.50, and I'm up to $6 now. And by the time I see just a couple of steps, I see the type of function and all the behaviors that I need to account for. So my function, how about P for parking? And it's a function, and I could use T for time if I wanted to, so maybe I will just for fun. So it's an integer function, so I need to show the integer function, and there is no left-right shift on it, and the step lengths are 1s like normal, so I don't need anything inside the integer argument. So just integer function of T. It's got an upshift of 3, and when it jumps 1.5 times bigger than a normal jump. So I'll use a 1.5. And then that's the function. I don't know if any of you have ever taken cab rides in cities, but as soon as you get in and say you want to ride, they flip a little flag down and it starts the meter. And it's not a timed meter. It's based on how far you've gone. But in most large metropolitan areas, like if you're in Houston or Dallas or areas like that, you may only need to go a mile or two. And it's hot outside, and you don't want to walk that mile or two if you're a businessman. So you just hail a cab and jump in. And so our function would, again, just be a step function. And so we'll give ourselves a label. And so this would be a cost of taxi is what my graph represents. And my x-axis represents distance measured in miles. And my y-axis represents cost measured in dollars. And here's where it gets kind of tricky. So if I just get in the cab as soon as I close the door and he throws the meter, even if I just turn around and walk out, he's going to say that'll be $2.60. And there's usually a cop around so that if you contest him, he'll just call a cop for you. But you know, most people don't do that. Most people take Ubers anyway. So notice this is kind of strange. If I go from 0 up to 1/9 of a mile, so that would be like a block or two, then it'll cost me that $2.60. But if I go over that distance, if I go anything more than 1/9 of a mile, which would be probably a couple of blocks, then automatically it just jumps up another 30 cents. It jumps up to $2.90. And so anywhere for that next couple of blocks, it's going to cost me $2.90 for the fare. But if I go over that next increment, then it jumps up another 30 cents, and now I'm up to $3.20. And so again, what I would see is a step function. So these three examples that you see on this front page of this assignment are just places where we have step functions. A cabbie has a little meter that's computerized, and it's tied to his odometer, and he doesn't try to calculate the fare. He just looks down at the meter when you say stop, and it'll tell you how much you owe. And, you know, you're supposed to give the guy a nice tip, too. You always ought to tip people like that. So here we go. I know what my function is. How about T for taxi? And the input X represents a distance in miles. It's an integer function, so there's my integer function. Now here's the tricky part. Normal step lengths are length 1. These lengths are 1/9. They are a fraction of, and it uses a 9 multiplier this time. And the 9 multiplier doesn't make it 9 times wider. It's inside inverse. It's 1/9 the width of normal steps. And it needs a vertical shift of a 2.6, and it needs a jump of a 0.3. And it's not wrong if you want to write 0.30 there, but typically you don't put the zeros into mathematical formulas, and they don't add mathematical value. So those three problems were all about applications where you see step functions used in business finance. So the back page is about exponential growth. So this is a hot topic right now. And we would have, how about community COVID cases? And our y-axis is the number of cases. And because it's a 1-to-1 scale, I don't need to say that's measured in dollars or pounds or whatever that might be. But my x-axis is not just days, but days since May 1st. So that what that tells me is that May 1st is t equals 0. And so on May 1st at 0, it says I've got 3 cases. And then this is a strange little scale, but after 2.8 days, what a strange number. And typically, it's not like we've been able to measure that, but the people that are actually doing the science and data collecting know the mathematics of this, and they've determined that that's typically the time it takes for the number of cases to double is about 2.8 days. So with that in mind, after 2.8 days, my 3 is going to become 6. And then if I go 2.8 days more, that would be 5.6 days. And after 5.6 days, then my 6 will have turned, it will have doubled again, and my 6 will have turned into 12. So every 2.8 days, the number of cases will double. So as a function, how about C COVID cases as a function of time? So this is a doubling exponential. So it'll be a base 2 exponential. And I need to make my graph 3 times taller than normal. So that's my 3 that I would use right there. And I want to make my graph 2.8 times wider than normal, because usually it takes 1 unit of x to make the values of the function double. So how do I make my graph 2.8 times wider? And that's inside inverse, 1 over 2.8. I've gone to the Desmos graph, and I have put in the requirements, the a value of a 3 and the b value of 1 over 2.8. And just to notice, that gives me an initial number of cases of 3. After 2.8 days, it's doubled to 6. 2.8 times 2 is 5.6. So after 5.6, I've doubled up to 12. So that confirms that I have the right equation. It looks pretty flat, but here's the thing that you always have to realize about exponential graphs, and this is the scary part of epidemics. Notice that those 3 cases, by the time I get to May 21st, look how many cases I have. So by May 21st, I'm way up here. I've got hundreds of cases. And that's certainly what happened in Amarillo since the initial cases, rather, of COVID-19. So we're convinced that this is a valid model. Our graph would look something like this. And of course, when I draw it in this scale, it does look like it's growing pretty quickly, and it is doubling every 2.8 days. So how many COVID-19 cases would there be after 21 days? So I would simply evaluate my function at 21, and that would simply be 3 times 2 to the 1 over 2.8 power times 21. And again, that's going to require a calculator. So I put this expression into my TI-84, and the answer that I get is 543. So that would be 543 cases. If you ever watch the news about the COVID-19 outbreak, you'll always hear the doctors say, our modeling indicates. And they're just trying to predict the future with what they've experienced with past epidemics and the way that epidemics are modeled. And they're typically modeled by these types of exponential functions. And that's assuming that there's a natural progression of the epidemic. And that's why we do things like social distancing, or do things like just trying to completely isolate ourselves so that there is not the common spread of the disease. So one more problem. The active ingredient in Aleve is naproxen, and it's sometimes called an NSAID, a non-steroid anti-inflammatory. And it has a half-life of 15 hours. You take them in 220 milligram capsules, and if you take 2 capsules, you'll have 440 milligrams in your body. And it's a decay curve because every so long, the amount of naproxen is cut in half in your body. So you've taken your 2 tablets, you have 440 milligrams in your body. So this is going to be a leave in the body. Our x-axis is time measured in hours, and our y-axis is naproxen measured in milligrams. So it says it has a half-life of 15 hours, meaning after 15 hours, then your 440 has cut in half to 220. So the next point on the curve is here. After another 15 hours, so this would be 30 hours now, 1 day and 6 hours, the 220 has been cut in half to 110. If I wanted to go another increment, then I could go 15 more hours, 45 hours. That would be nearly 2 days. And that would cut in half again. So the 110 would now be cut in half to a 55. And it would continue that way until virtually all of it has disappeared from your body. So as an exponential decay curve, it would look kind of like this. And how about N for naproxen, and it's a function of time, so let's use T. It's a base 1/2 exponential function. So it has a vertical stretch factor. Normally the y-intercept is at 1. Our y-intercept is 440 times larger than normal. So we'll have a 440 vertical stretch factor, and our function is 15 times wider than normal. So we use inside inverse, fraction 1 over 15. So how long will it take for the concentration to reach 100 milligrams? Notice on the graph that at 30 hours, it's down to 110, so it should be something in excess a little bit of 30 hours, maybe 34, 35 hours. But the only way that we'll find that is to actually solve this as an equation. So we would have 100 is equal to 440 times 1/2 raised to the power of 1/15 times t. So again, the first thing we do is we'd divide by 440. In our next step, I'm going to reduce my fraction and just call it maybe 10 on 44. I could reduce it to 5 on 22, but or I could leave it as 100 over 440. It really wouldn't matter. But that would equal 1/2 raised to the power of 1/15 t. And the next thing I need to do is to reverse the 1/2 exponential with a base 1/2 logarithm. So I need to use a base half logarithm on both sides. The next step would say the base 1/2 logarithm of, I'll go ahead and call that 522 because I just like to reduce fractions. So I've divided the 2 out of the 10 on 44, and then that would equal 1/15 times t. So the next thing that I would do is to multiply both sides by 15. So since I'm out of room here, I guess I'll have to do it this way. I'm going to multiply both sides by 15. So that will say 15 times the base 1/2 log of 5/22. And by the way, if you wanted to, you could still have that as 100 over 440. This will be so confusing if all you do is look at the key. Would equal t. So there's another classic case where I'm going to have a calculator. And after I punch this into my calculator, out comes the answer. t is equal to 32.06. I think I'll call that 32.1 hours. And that certainly confirms what we thought on the graph, is that it would be something just a little past 30 hours before it reached 100 milligrams. So those are the ways that the horizontal and vertical stretch and compressions come into play in applications. And if you understand your inside-outside rules, then it's easy to take any parent function and cause its characteristics to model some phenomenon that you can see. And so obviously, if you get into any of the math or science majors in college, you'll study this again in the appropriate class. Well, hope to see you soon. Bye-bye.